In this video, I'm going to give you a brief introduction about contentos and the technology behind it. This video is tech-oriented, so if you're curious about how contentos works, or if you're a developer who wants to contribute to contentos project, this is the right place to start. So, what exactly is contentos? Well, contentos is a layer 1 solution aiming to form the foundation for a decentralized digital content ecosystem that empowers everyone, including creators, consumers, and advertisers, to earn fair compensation for their contribution. The problem of current content ecosystem is that they're usually run by centralized platforms that depend on advertising for revenue. Content creators are therefore pressured to produce content that is approved by advertisers instead of following their creative muses and expressing themselves freely. The constraints inherent to ad-driven content platforms begs the question of just how much freedom of expression is actually allowable. And it's imperative to ask the question, where is the majority of the money going? Simple. The money goes straight to the centralized platform. And this is why we built contentos in the first place. Now, if you take a look at this picture, the bottom part is the contentos public blockchain, and above it are the dApps. And currently we have 4 different dApps built on top of contentos, and all the users can interact with the contentos blockchain through the dApps. Now, you're probably still confused about how this all works. Well, you can think of it as an enhanced version of Steemit, where users can upload videos or post an article, and other users can view the contents, hit the like button, or leave comments. Simple as that. And all the users involved will get rewarded. As you can see, everything, including the financial activities, are totally governed by the decentralized contentos platform. Everything is transparent and there is no third party to take a cut. All the money goes straight to the end users and the contributors that we call the blog producers. Now that you have a basic understanding of how contentos works, you might ask yourselves, we already have Steemit, why do we need contentos? As I mentioned earlier, this is a tech-oriented video, so I'll try to answer this question from the perspective of an engineer. Alright, these are the 4 tech features that I wanted to talk about today. Free transaction, parallel execution, self-adaptive BFT, and smart contract. Okay, let's move to the first tech feature, free transaction. If you do a little research, you'll notice that almost every other blockchain project charge users a certain amount of fee every time they send a transaction. Part of the reason is that if you have 0 transaction fee, you're literally inviting other people to perform spam attacks on you. So you might be wondering if there is a way to have 0 transaction fee yet to avoid the spam attacks. Here's how we do it in contentos. As you can see, a transaction would require 2 kinds of resource, net resource and CPU resource. And all these resources will be converted into something called stamina. And in contentos, every user has exactly the same amount of stamina called free stamina. So every time a transaction is sent, a small part of the free stamina will be used. And if the user keeps sending and sending, then eventually all the free stamina will be used. And at this point, this user cannot send more transactions. This leaves him 2 choices. One, he can just wait for 1 day so that all the free stamina can be restored, or 2, he can put some of his token on stake. In exchange, that user will get something called staked stamina. Now the more token he put on stake, the more staked stamina he gets. And the token he put on stake still belongs to that user, and it's just temporarily frozen. And that user can claim his staked token later if he need to. That's it. Very straightforward. Simple proof of stake. Now moving to the second tech feature, parallel execution. A block usually contains multiple transactions. In most cases, all those transactions are executed one by one in a serialized manner. The reason of that is because some of the transactions might be related, and it's very important to preserve their orders. The problem is, in most blockchain projects, the software just cannot know in advance which transactions are related and which are not. So to play it safe, all those transactions are executed one by one in a serialized way, which is a complete waste of the modern multi-core CPU architecture. To solve this problem, we introduced something called batch preprocessor. Now, before all the transactions are executed by the executor, they have to go through the preprocessor. It will try to find out which transactions are related and put them into the same transaction group. So when this is done, all the transactions are put into different transaction groups. Transactions in the same transaction group are considered to be related. Uh, those that are in different transaction groups are not. So uh, they can be executed concurrently. Let's take a look at the example below. Say there are 4 transactions in one block. Transaction 1, 2, 3, 4. In transaction 1, Alice transfers some token to Bob. In transaction 2, Bob transferred to Charlie, and David to Ed, Fred to George. You can probably tell that the first 2 transactions are related because they both involved Bob, and that's why they're put into the same transaction group. In the meantime, transactions 3 and 4 are not related, so they're put into different transaction groups. So in this case, we have 3 different transaction groups. So it's natural that we can start 3 threads to execute these transactions concurrently. Okay, moving to the next tech feature, the consensus. But before we get to that, let's see how most of the consensus protocols that use BFT in other projects work. These protocols are very similar, and I call them conventional BFT or serialized BFT. They all have one thing in common, that is, the block generation and the BFT voting process are synchronized. Here's how they usually works. Um, First, the system generates a new block, and then it starts the BFT voting process, which is a 3-phase protocol. And when this is finished, which means the last block is confirmed, and only by then the system can start to generate a new block. The problem of this approach is that the 3-phase protocol usually takes seconds to finish, so during this time, the system is just not, well, it's still sending and receiving transactions, but it's just not generating new blocks, which compromise the throughput of the whole system. There are some ways to eliminate this defect. At the right side of this graph is something that I call the pre-generation. So whenever a node receives a block, it just applies the block first, even if it's not confirmed, and then it starts to generate the next block, which is called a pre-generated block. Remember that I mentioned this process can be really time consuming, so during this time, what the node is doing is just keep adding new transactions into this pre-generated block. And when this is finally over, the nodes just adds a signature to this pre-generated block, which is called finalizing the block, meaning that this block is officially generated. But the solution brings many other problems which are out of the scope of today's discussion. To solve all the problems we mentioned above, we invented something new called the self-adaptive BFT. As you can see at the left side of this graph is something called the depos routine. What it does is to generate a new block every second in a depos manner. At the right side is the BFT routine, which always tries to reach consensus on the head block. Well, it's actually a little bit more complicated than that, but for simplicity, we just assume that um, the BFT routine always proposes the head block. These two routines are completely decoupled and work in an asynchronous way. The depos routine is always generating blocks despite the state of the BFT routine. That's why it has higher throughput than conventional BFT because there is no waiting. You're probably still wondering why is it called self-adaptive BFT? I think this can be better illustrated with this graph. So at the left side are a group of nodes called validators. A validator is a node which is responsible for block generation and block confirmation. Here C1 in this gray circle means that block 1 is confirmed at this time. And this means that block 4 is confirmed at this time. As you can see that after block 1 is confirmed, the next confirmed block is block 4. Block 2 and block 3 are skipped, which is okay because if you really think about it, that block 4 is built on top of block 3 and block 3 is built on top of block 2. Meaning that if you confirm block 4, that all the blocks before it will also be confirmed. So in self-adaptive BFT, not every block requires to be confirmed. That's why it's called self-adaptive. Now normally if everything works fine, all these blocks will be confirmed within 1 second. However, when the system load is really high or there's something wrong with the whole network, the BFT routine cannot reach consensus within 1 second. In this case, some of the blocks confirmation might be skipped. The last feature is smart contract. Contentos use WebAssembly as the virtual machine, so it's very similar to EOS smart contract. If you already know how to build a smart contract on EOS, then you'll have no problem writing smart contract on Contentos. The procedure is pretty much the same. Step 1 is to write a smart contract in C++. And step 2, build your smart contract to generate the ABI file and WASM file. And step 3 is to deploy the generated file on Contentos. And after the files are deployed in step 4, users can interact with their smart contract by sending transactions. Unfortunately, I'm not going to cover everything here, so if you want more details about building a smart contract on Contentos, I suggest you to read our documentation. Thank you.